Here we will consider a first order differential equation of this general form. So the right hand side is some function of x times some function of y. So examples of differential equations of this form are dy dx equals x squared y cubed, dy dx equals y squared sine of x, and dy dx equals y times ln of x. So we have some function of x times some function of y on the right hand side. Now here's an example of an equation that is not of the form dy dx equals f of x g of y. We can't write x squared plus y cubed as a product of function of x and a function of y. So let's look at some examples. This first differential equation here can be written as a function of x times a function of y if we write it like this. We cannot, however, write the second equation in that form. What about this equation here? Well, we get dy dx on its own, subtract 3x from both sides, so we get 7 minus 3x on the right hand side, and divide both sides by y. So now we have it in the form of a function of x times a function of y. Now, of course, our dependent variable doesn't have to be called y, it could be called z, theta, or v. Similarly, our independent variable doesn't have to be called x, it could be t or r for this differential equation here. Okay, so let's go back to using y for the dependent variable and x for the independent variable. So let's suppose our differential equation has this form here. How would we solve it? Well, what we do is we separate the variables. We bring everything involving y to one side and everything involving x to the other side. So we divide both sides of this by y and we multiply both sides by dx. So we'll end up with dy over gy equals f of x dx. So we could just bring the gy, we could just swap the gy and the dx, just swap those terms actually to separate the variables. So we have y on one side, x on the other side, and then we just stick an integral sign in front of both sides. So we have to integrate 1 over gy with respect to y, and we have to integrate f of x with respect to x. Let's take this example here, dy dx equals 3x squared over y. We can see the right hand side can be written as a function of x times a function of y. So we can write it as 3x squared times 1 over y. That's the right hand side. So that means we can rearrange this to get y on one side and x on the other side. I suppose the quickest way to actually rearrange this differential equation is just to cross multiply, because we have a single fraction on each side. So y times dy equals 3x squared times dx. Next we integrate both sides. Now if we integrate y with respect to y, we add 1 to the power, so we get 1 plus 1 is 2, and divide by the new power we get a half y squared. We do have a constant of integration here on the left hand side, but I'll get back to that. If we integrate 3x squared with respect to x, we add 1 to the power, so we get 3 thirds x cubed, or just x cubed, and we have the constant of integration. Now what we do is we imagine taking the constant of integration that is actually there on the left hand side, bringing it over to the right hand side and combining it with the constant of integration on the right hand side, and we call the result plus c. So for example, if a was the constant of integration on the left hand side and b is the constant of integration on the right hand side, then c would be b minus a. But since both a and b are constants, then obviously b minus a is a constant, so we call it c. Now we can then get y as a function of x, so this is the solution to the differential equation. In this example we can see the right hand side is a product of a function of x and a product of a function of y. Like the previous example, the quickest way to separate the variables is simply to cross multiply here. Sine 2y times dy equals cos of x times dx. So actually this is what I just said, this line here. This is the result of cross multiplying, is the quickest way to do it. Then we just integrate both sides. If we integrate the sine of, well, if we integrate function, we get the minus cos function. So if you look that up in tables, the integral of sine is minus cos. But then we have to divide by the coefficient of y, which is 2. Because if we differentiate this by the chain rule, the derivative of cos is minus sine, then we must multiply by the derivative of the angle, which is 2. The 2 cancels with the half here, so we'll end up getting back plus sine 2y. The integral of cos 1x is sine of x. You can look that up. And again, we have two constants, but we just bring the constants to the right hand side and call the result c. Finally, we can get y as a function of x. We just multiply both sides by -2. So this is what we'll get, and we then have to get 2y by taking the inverse cos of all of this, and the last step will be to divide both sides by 2. Now, since c is a constant, obviously 2 times c is a constant, so we could rename this d. We don't rename it c because then it looks like c is equal to 2c. So we just give it a different name. Well, we use a different letter from c, so we can say d or e or whatever we like, just as long as it's understood that we have a constant here. Now let's look at this differential equation here. Now it turns out we cannot separate the variables. We cannot write the right hand side of this equation as a function of x times g of y. If we could separate the variables. That's not possible. However, we can change the variable, make a change of variables in this differential equation so that we do get a separable differential equation. What we do is we let y over x equal a new variable which we will call z. So you see, y squared over x squared will be z squared, and y over x will be z. So the right hand side will be straightforward. The right hand side will be z squared plus z plus 1. Now what about dy dx? Well, we can rearrange this to write it as y equals z times x. Let's differentiate both sides with respect to x. So differentiate y with respect to x, we get dy dx. And we use the product rule here because z is a function of x, and x is obviously a function of x. So we take the first function times the derivative of the second function. So z times the derivative of x with respect to x, well, that's just 1. Plus the second function x times the derivative of the first function with respect to x. So we're using the product rule here. So now our differential equation becomes, well, on the left hand side we have z times 1 plus x times dz dx, and on the right hand side, as I said earlier, we have z squared plus z plus 1. We are going to solve this equation to find z as a function of x. The dependent variable is now z, the independent variable is x, and once we found z as a function of x, we can get y as a function of x just by multiplying x by our function z. So we see in this differential equation we can subtract z from both sides. We can multiply both sides by dx over x. That'll get rid of the x over dx on the left hand side. So I'm going to bring the z's to the left hand side, and we need to also divide both sides by z squared plus 1. Okay, so if we multiply both sides by this thing here, we can separate the variables. So if we multiply this thing by x dz dx, well, as I said already, the x times dx will cancel with this, and we'll have 1 over z squared plus 1 times dz. So I'm just multiplying dx over x by x over dx to cancel them off, and I have this brought in as well. Now if I multiply the right hand side by this thing here, we'll cancel the z squared plus 1 on the right hand side, and we're left with dx over x on the right hand side. So the next step then is to integrate both sides. So now this integral on the left hand side is a standard integral. You can look this up in tables. It's got the form 1 over a squared plus u squared, where a is a constant. The variable u in our case is z. So a squared is 1 compared to our example. U is z. So we can see the answer is 1 over 1 inverse tan z over 1. So it's got the form 1 over z squared plus 1 squared. So a is 1. And of course we have a constant of integration here. I'll just put it in for now I've explained this already. Over here we have the integral of 1 over x with respect to x, and we know that that's ln of x, and we have another constant of integration on the right hand side. But as I said earlier, when we bring the a over, we get b minus a, and that's just a constant, so we call that c. So the constant doesn't appear on the left hand side, so I'll call the constant of integration c. Well, it doesn't matter what you call it, just put it on the right hand side. So now we can solve for z, just get the tan of both sides. So we get tan of ln of x plus c. Since y equals z times x, we can write down the solution of our original differential equation. It's x times this here. If you want to, you can write this general solution in this form here, x tan ln d of x, where d is a constant. Why can you do that? Well, we have the log of a product here, the log of d times x. We can write that as log d plus log x. It's one of the rules of logs. Now, since d is a constant, well, ln d is actually equal to c here. So d is such that ln of d is c. Let's take one more example. We here have an LR circuit where L, the inductance of the inductor, is a constant, or the resistance of the resistor is a constant, and the voltage source is a constant, E. From Kirchhoff's law, we know that the sum of the potential drops over these two components must equal the voltage source E. So the potential across the resistor is current times resistance. The potential across the inductor is inductance times the rate of change of current with respect to time. Now, we want to separate this differential equation so that I is on one side and t is on the other side. Let's see that this differential equation is actually separable. Well, we subtract IR from both sides. Next, we will divide both sides by L. So we can see that the right hand side can be written as a function of I times a function of t. Well, the function of t is just 1 here. You know, we can call this our function of I. E, L and R are just constants. So this is our function of I. And our function of t is just 1. So, as we've seen before, if we can write it like this, then we can separate the variables. Well, all we do is interchange dt with what's in the brackets here. So we get di over E over L minus I R over L equals dt. So this is the result of cross multiplying and rearranging. So we just have I on one side now and t on the other side. So how could we make this a little bit easier to read? Well, we could maybe multiply both sides by 1 over L. So we get di over L times this thing here. Well, that will just give us E minus IR, and we multiply the right hand side by 1 over L. So multiplying this by 1 over L and this by 1 over L. Now we can integrate both sides. We can use this result here to perform this integral. We can see that this has the form 1 over a constant times our independent variable. So it's 1 over E plus the constant is minus R, and the variable is I. Well, it's the dependent variable actually, I. Now, so it's 1 over B, where B is the coefficient of I, so it's 1 over minus R times ln of this denominator, E minus IR. So that's a standard result. You can check that by differentiation. Apply the chain rule. The derivative of ln is 1 over the argument, 1 over a plus bx, and then we multiply by the derivative of the argument, which is b, and b's cancel here. Anyway, we get a constant here, but we bring it over to the right hand side. If we integrate 1 over L with respect to t, we get 1 over L times t, or just t over L, and the two constants are brought to the right hand side, so let's call them c. Now we can multiply both sides of this equation by minus r to get this here on the right hand side. We want I as a function of time. We want the solution is the current as a function of time. That's the solution of our differential equation. So we raise e to the power of both sides here. That's how we get at the argument of the ln function. Over here we divide both sides by minus r, so we get minus e over minus r. That's just plus e over r, and then we have the exponential term divided by minus r. Now I will impose a boundary condition that I didn't mention earlier. That is, the current at time 0 is 0. So the current is a function of t. So there's the independent variable t. Everything else, they're just constants. So this is I as a function of time. This is the general solution. But we want I at 0 to equal 0. So we plug 0 in for t, so we get e to the minus rc here over r. And solving this, we multiply across by r to get this equation. So now we can see that e to the minus rc can be replaced with e in our solution. We can write our general solution like this over here, so I'm just moving it over here. We can factorize the exponential term like this here. We just add the powers to get this back, of course, but we now replace e to the minus rc with e. Finally, we can factorize out e over r to get our final solution with the boundary condition that I at time 0 is 0. Because the power here is negative, we can see that as t goes to infinity, for long times, the current I is approaching the value e over r. So this is going to 0.